Okay, so this gives us an introduction of how a moving charge responds to a magnetic field. Where do magnetic fields come from? Okay, well, magnetic fields come from moving charges, so that moving charges create magnetic fields, and moving charges respond to the force of respond to magnetic fields with a force. Okay, we've got that part. Here's the origin of magnetic fields. Now, this is very much analogous to the electric field of a point charge, where you have K times Q over R squared, or K times Q over R squared multiplied by your unit vector R divided by magnitude of R. And the text actually uses R hat for this vector, this unit vector R over magnitude of R. So your text might write this as QV cross R hat divided by R squared. Just like the law for the force exerted by an electric field, it's an inverse square force. Okay? The difference is we have a cross product with our unit vector as opposed to the expression for the force due to an electric field, or the electric field due to a point charge. I'm going to write that down just for comparison. And now you can see that we have KQ over R squared multiplied by R divided by its magnitude. Here we have a K prime instead of a K. Instead of a Q, we have QV. And instead of multiplying by R divided by R, the unit vector, we take the cross product of QV with R divided by its magnitude. And then that's divided by the square of the magnitude of the R vector, just as it is here. So the difference is the cross product as opposed to the product, the K prime as opposed to the K, QV instead of Q. So this might be a typical situation. We have a vector QV, and this isn't regarded as being in the X direction. It could be just about anywhere anywhere where the X component is positive. We don't know where this projects to the X-axis, if it projects up to the XY plane or down to the XY plane, because we don't know what the perspective of our three-dimensional coordinate system is. Okay, well anyhow, this represents a vector. R represents a vector from the position of the charge to the position at which we want to calculate the field. Okay, so we did define the R vector up here, but here it is. It's the vector from wherever the charge is to the vector which we want to calculate the magnetic field. And it's going to have the direction of QV cross R. Now, depending on the direction of QV, let's just say that QV is down this way, and that the particle is here, and that we're looking at a point out here. Let's say here. So to cross this vector into this one, we're going to have to tilt our hand a little bit to get up to here. And our thumb is going to tilt out this way a little bit, so that the magnetic field might look something like this. It's going to be perpendicular to R. It's also going to be perpendicular to the direction of the Q vector, the QV vector. So if I draw a dotted line parallel to the QV vector, we would have a right angle here. And I've drawn that very faintly because I could easily really mess up this picture. Okay, that's the idea. Okay, so, and then R divided by R, and I could say that's, if you want, R hat is the unit vector in the direction of R, so that the R over R, or if you prefer R hat, goes here, QV vector here, and the magnitude of R is squared here. In other words, the distance here is squared.